Well, thank you very much for the kind introduction, and I am here today to show you the results from a study that we have performed on adsorption of gold clusters to molybdenum deselenides nanoflakes. Well, why is it important to study such composite systems? Transition method ecogenides nanoflakes have drawn much attention in the recent literature because they are suitable for a wide range of applications which span from sensors like electronic devices to energy like the hydrogen reduction catalysis. And they are produced by two kinds of synthetic procedures. One of them is top-down synthesis and the other one is bottom-up. The bottom-up syntheses are based on the building your material from its forming molecules, and top-down synthesis is based on the opposite. So I have selected here two very used methods. One is the chemical vapor deposition, in which you begin with the molecules being formed on the gas phase, and then you form your nanoflake, which is a bottom-up synthesis example. But if you have your bulk material, like in here, you have a trigonoprismatic 2H phase, and then you can adsorb lithium in here in solution, and then exfoliate that with an electrical current, and you can obtain nanoflakes of, in this case, 1T octahedral nanoflakes. Meanwhile, if you put those materials, those nanoflakes, into contact with metals, you can produce hybrid dimensional materials, which are important for applications, in particular in photovoltaics, since you can make with those materials Schottky contacts, and you can also make some water splitting devices, like the one illustrated in here. It is noticeable that once you have your nanoflake, you can have two kinds of contacts that you can make. Here I am taking just one example of the two polytypes, 2H and 1T prime. In this case, you can put your cluster or surface or a datum in here interacting vertically or in the edges. If the interaction is vertical, then the vertically stacked metal cluster or surface will interact just with complete valence atoms, whereas if they interact with in the edges, they will interact with non-complete valence atoms, which you can call dangling bonds. And those architectures are used for those devices, and you can modulate the behavior of your devices by putting your metal, for instance, in contact with each region of your nanoflake. So what do we know about those nanoflakes? Well, actually, we know how to modulate the kind of nanoflake that we can obtain, for instance, in CVD method, just by varying the synthesis temperature. We can obtain one or other polytype, and the theoretical counterpart of this knowledge has been produced very recently by our group in 3 papers, 2 of which are published last year, one that's submitted that we have already established here in this first paper, that the edge formation energy, which is the energy of a particular relaxed nanoflake minus the energy of the periodic phase, is the main stabilizing factor that stabilizes 1T prime nanoflakes in relation to their 2H counterparts in the smaller sizes. And there is a there is a energetic transfer, and we have established that 2D nanoflakes, when compared to their 1D counterparts, are stabilized by a combination of effects of charge, edge charge modulation, and the octahedral distortion of the core atoms. And furthermore, we are submitting a study, we have submitted a study in which we stabilize an investigation that tries to correlate how the shape of the nanoflakes stabilize them. But what we do not know is that, as I have shown you, by making heterostructured materials, we can reach a lot of applications. However, it's fundamental for us to develop the atom level knowledge of how this kind of interaction, metal and nanoflake, is done, what is the nature of that, for us to design efficient materials and to understanding the chemical basis, the basic chemistry of that is the objective of my work. So we try to answer those three questions: how the physical-chemical properties evolve as function of TMD, transition metal, decalcogenide, polytype, and gold geometry. What is the binding mechanism of the system, and how do these systems behave with small nanoflake sizes? The choices that we have done are based like this. We have taken all four clusters, which is the smallest magic number for gold clusters, and the magic number is a particularly stable size of the system that we have. And we have also selected 1T. I have put here 1T prime because in the course of the optimization, the phase distorts to its distortion octahedral phase. And we have taken 1T and 2H polytypes, and 16 and equal 16 is also a magic number. So they are very stable systems, not in contact. So this is important to take this kind of system because we can see how those particularly stable systems change their geometry due to the adsorption. We have also taken nanoflakes 1T and 2H with size of 36 formula units to see if putting further apart those edges within the nanoflake would change the general trends, the general physics of our system. We have performed for these 16 formula unit nanoflakes method of generating the structures, which is composed of 3 steps. First one is to generate the adsorption probable structures by randomly adsorbing the gold cluster on the surface of the nanoflake, then taking this huge set, which has been considered with 20 million configurations, comparing them by the modified Euclidean matrix, and reducing them to the 20 most dissimilar configurations, and then taking this reduced set and performing the DFT calculations. We have taken those 20 most dissimilar configurations for any particular nanoflake polytype and initial gold geometry. So as we are working with 2 gold cluster geometries and 2 polytypes, have done initial set of 80 structures for N16, and with the knowledge gained here, we have proposed a set of structures for N36, being N the number of formula units within our nanoflakes. What we have observed here is that we have the total energies in here. Those are the relative total energies of our sets, and we have divided both of our sets with the 8 most dissimilar groups of the optimized adsorbed systems, and these sets have been a result of the application of a chi-means clustering method developed by Professor Marcus Kilis. And we can see that first things, the most notable is that there is an energy gap in here, and the most stable systems are composed exclusively by 1T prime nanoflakes. And within both sets, it's mix of the initial gold cluster geometry. The initial geometries of the gold clusters are mixed. And we can see that this is the energy gap separating on the sizes due to the panel of the nanoflake sizes. They are respective. They decrease as you put the gold into contact with the nanoflake. Furthermore, by analyzing the topology of the curve, you can see there is there are more dissimilar groups here in this 2H region, which is due mainly to the fact that the distortion taking part on 1T prime nanoflakes is dominated by just one mechanism, whereas the kinds of distortions that you can have on 2H nanoflakes in here are more abundant. Therefore, the topology of the curve here on the 2H region changes in relation to 1T prime. We have also seen how the structural properties change, and we have seen how the average bond length, the effective coordination number, and the distances of the closest gold atom to the closest molybdenum and selenium atoms change. And we have seen that the size doesn't influence very much on the variations of those properties. However, you can notice that there are completely opposite behaviors on the delta DEV and delta ECN on 1T prime and 2H regions, which are due to the fact that if I can get 1T prime nanoflake, there will be no matching of the selenium on the edges. So the interaction taking place there is interaction between the edge selenium on the gold, and whereas on the 2H nanoflakes, I will have to balance those interactions because there will be on the edges the selenium-selenium interactions, which are matching on the edges, and the selenium-gold interactions. Therefore, the general evolution of structural properties is modulated by edge effects, in particular the edge configurations belonging to each nanoflake polytype. Electronic properties we have seen, which is the near homo levels are dominated by the levels belonging to the nanoflake and not of the gold. Gold clusters participate in here in a region below -1, -1.5 electron volt. And we can see that if you analyze just the near homo region in here, the change, the electronic properties that occur due to the adsorption is a shift of the levels of the nanoflakes to lower energies. And that's the electronic factor that's associated for you to absorb your gold cluster. The lack of splitting in the levels in here indicate that there are no covalent bonds being formed as you make your your adsorption. Furthermore, we have seen how the charges vary as you make your adsorption, and we have seen that you have here accumulation regions intercalated with depletion regions. Accumulation is red, depletion is blue, and here we observe charged dipoles, which is consistent with your analysis. So we could divide the total energy of our systems into distortion energies, which are the total energies of the system distorted minus their energies with the relaxed systems in the isolated cases, and the interaction energy, which is the total energy of the system minus its distorted parts. And we see that the systems operate in compensation mechanism between the distortion and the interaction energies. Thus, the binding mechanism yields those kinds of values. And the adsorption energies for 2H nanoflakes is more intense than for their 1T prime counterparts. However, those counterparts cannot compensate the edge formation energy. So that's why we observe for the lower part of the energy curve exclusively systems which are composed exclusively of 1T prime nanoflakes instead of 2H nanoflakes mixed or something like that, or even 2H systems being the most stable despite the values of adsorption energy. And then we have established the interplay between interaction energy, the energies of formation, and the edge energies. We have established the binding mechanism, and we have seen by the variations on the physical-chemical properties, we have obtained a deeper knowledge on the adsorption of gold to molybdenum diselenide nanoflakes. Thank you very much, and thanks for the financing agencies and for your attention.